Welcome back. This is the second video in our series on the HEC-Commander Tools. These are automation tools for HEC-RAS and HEC-HMS workflows that were authored with ChatGPT assistance by C.H. Finstermaker & Associates. I'm Bill Katzenmeyer. I'm the author of most of these tools, and we're building all these tools to help with our Louisiana Watershed Initiative Region 4 efforts. Today we're going to cover Raz Commander, which is a script for parallel HEC-RAS execution in a Windows native environment. It supports all HEC-RAS versions, doesn't require any proprietary software, has the ability to engage remotely, directly network attached machines for remote computability, to engage multiple machines to act in parallel to complete a set of runs. So the basic operation of these scripts is we've got our user input and our settings. The script does a file deploy and copy to copy all the HEC-RAS projects out to different machines and different locations, creates batch files, command line executes those batch files, and then performs the results collection. This also is now supporting 2D infiltration parameters and override regions, which are fun. We'll cover that in the next video. This video is going to cover 1D HEC-RAS modeling. So how do we parallelize? The existing solutions are either all built on Linux or the cloud, or try to leverage HEC-RAS controller. Well, HEC-RAS controller is using HEC-RAS's abilities. It's essentially an API for accessing HEC-RAS features, but parallel operation is not a feature that HEC-RAS has. So we have to build scripting around it to be able to affect that ability. So the market solutions, again, don't have access to the latest versions because they're generally based on Linux. They're much more built towards mass simulation runs, thousands and thousands of runs, versus I think for most consultants we're dealing with hundreds, or within an order of magnitude of 100, so that you can reasonably do these with batch sets of 100. None of those market solutions are free. They're all proprietary. They all cost money. Most of them involve the cloud, which I think I've covered in some of my blog posts. Very prohibitively expensive, which also requires data transfer, which then involves more bottlenecks and time. So a better solution was needed. We had already had our local modeling machines, so we decided to try to first run as many runs on a local machine as possible, but then also engage multiple remote machines. So for our setup, for local compute only, you just need VSCode, Anaconda Navigator. If you're trying to do remote computation, you're going to need to set up a Windows file share. You got to be able to push those folders over to that remote machine. You also have to go accept the HEC-RAS terms and conditions as your user on that machine. That's something you can't get around. You also need to set up remote access. You need Windows RM admin access, as well as remote access to the machine, so that you can run things through PS exec. And that's something we'll cover, but your IT needs to make this available to you. Otherwise, you won't be able to run things on multiple machines without doing it manually. So let's get right into it. Now, if you were here for the last demo, it's the CSV file with all of our run parameters, all of our user runs. We created 20 runs. Our HMS has completed. We've got 20 DSS file outputs, and under normal circumstances, you would need to go open HEC-RAS, create a you would need to create a plan for each one of these. You'd have to create a plan file, U file, everything for each one of these. So our current 1D model just has all of our unsteady flow data. All of our subbasins are mapped as flow hydrographs into the model. Uniform flow hydrograph, upstream flow hydrograph, all the different types, but they essentially point back to the file as well as a path. And so the file, well, we've got that file. That's what we're changing. And so it's very simple to just change out the files, change out the U files and continue on. So the correct way to set up this model is go into options, computational options, tolerances, make sure that you're using the correct number of cores. In our case, we're going to use 2. 1 to 2 is generally the best for efficiency if you're doing parallel runs. If you're doing one run at a time, closer to 8 is fine. But just know that once you get past 2 cores, it's not using those extra cores very efficiently, and so you can get a lot more throughput out of a machine by running 4 or more at 2 cores than trying to run it, say, 4 or 8 or even 6 cores. Of course, your model needs to be able to run, so if I click compute and this doesn't run, it's not going to run with my automation. So ensure that everything's set up here, your flow output locations, anything else that needs to be done. This is your template. This template will be copied and all settings will be copied. The only thing that'll be changed is the DSS file. So click the advanced user button, takes you to the RAS folder, which is, again, just in our submittal folder. We've got 2 plans, 1 geometry, and 2 U files. Let's take a look at those U files. Let's see the DSS path right there, easy. DSS file right there, easy. So that's what our script is changing. That's what we're working with to actually get Raz Commander to operate. So let's open up Raz Commander. This is our 1D version. It's Raz Commander 1.0. Again, if you go to the website, just did this for our previous videos. Let's go back again. Go to HEC-Commander. Go to the Raz Commander subfolder. Raz Commander 1.0 right there. That's the one all-in-one script for everything. We've got program outlines. We've got other inputs that are needed for our other modes of operation. But you should be able to go right here, click, go to the 3 dots, go to download, and get that file. So just like our last script, we come to our left-hand side and we click all the way down. Here we've got some outputs, so let me clear those outputs. Okay, so we got 14 code cells. It's a lot. It's a lot here, but there's a lot of value too. Let's go over these user inputs. The very first thing that we have in this Raz Commander user inputs, and one thing that's important to know, all these user inputs are the primary user inputs. There is a GUI that pops up later. It populates that GUI with the inputs that you placed here as text. So if you want something to default to something that's a little closer to your actual folder or to not require you to change anything in the GUI, set it directly in this user inputs box. Otherwise, you can always just set it in the GUI, although it's a new feature. I prefer if everybody just uses the text and uses the GUI to check it. I think that's the better way at this level of sophistication of this script as it stands currently. We've got 2 modes. The first is run missing, which is very similar to the HMS-Commander script. It will not change anything. It will not build new plans. It will just take your existing HEC-RAS project folder and run it. So this would be useful if you've got another project that or another, say, program that generates lots of HEC-RAS plans, but you just need a way of parallel running it instead of running it in series like you normally would have. Well, this script allows that. You go to run missing. The one thing that you need to be aware of is it does look for the DSS file output. So if you, for whatever reason, use another method and you don't specify different DSS files for each plan's output, this script is going to be confused because it's looking for the DSS file outputs to decide whether or not to run any individual plan that it finds within the HEC-RAS project folder. It's hard to accommodate every use case with these, but I think there's enough value here that if you really need to use this, you can just rename the DSS lines, and that's something that we'll go in a future example how to do that. It's not really that hard with GPT and all these tools that we have. So the most powerful mode is the build from DSS mode. That's what we're going to be using today to build all of our new HEC-RAS project plans based on all those varying DSS inputs, where we varied all of the HMS parameters. And we want to test the sensitivity of those parameters through the HMS model, since that does all the routing. Next is our HEC-RAS project folder. You got to provide the full project folder. Here we are providing our 1D multi-parameter calibration. This is a folder I've already created and already, I didn't do any runs, but I did create this in a previous step. But this is actually our output folder. In build from DSS mode, your project folder is going to be where it builds your final project from a template. If you're in run missing mode, the project folder is the project that you want to run. So it's a little more apparent when you see the GUI, but the operation of the script is such that only these inputs are needed if you're in run missing mode. If you're in build from DSS mode, you add these additional settings. And if you also want to do infiltration layers, you add these settings, and they build incrementally. So we need to define deploy targets. So the way this script operates, because if you were to go and try to run in parallel right now out of a single HEC-RAS project folder, you were to open four instances of HEC-RAS and just click compute, 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 compute. Well, let's say that you didn't do the geometry preprocessor, or for whatever reason, you need to do the preprocessor. If you get to 2D and you're changing the infiltration parameters, you do need to do the preprocessor again. So for whatever reason, maybe even if it's just getting through that and just selecting the U file, if you do those all at once, you'll end up with file conflicts, whether it's from the geometry preprocessor or the .x file or whatever other files that it creates. So the most robust and easiest way to prevent that from happening is to just take advantage of the fact that storage is cheap and duplicate. At this point, you've got a template folder that you're trying to vary, that you just simply duplicate the project folder, let HEC-RAS run, and then bring the results back when it's done and delete the temporary folder. So in this case, you've got deploy targets. Well, these deploy targets are the locations of the temporary folders that hold your temporary copies of RAS while those copies run. So in this case, it's C auto RAS temp, and I've got a subfolder for this particular set of runs that I've defined. And then I've also got the ability here to define, you see I've got a long list of remote machines. This is where you can define the network path for the remote machines. So in this example, I've got HEC-03, which is another one of our workstations, and I'll go there, and I've got auto RAS temp. You can see actually I've got some temporary folders there from the last time I ran this. And so you'll see there it's quite a big folder, but that's we just buy the storage. It makes this a lot more powerful. Again, up to a 70% increase in throughput by using this method just on a single machine. And the ability to add additional machines with 100% performance improvement for each one for parallel runs is pretty powerful. So that's how it's accessing those remote machines, is through the network path. And so if you're providing to the script a remote machine to run, you've already gone through the setup, then you should have that path there, and you're going to want to define a subfolder within that for it to run in. You want to give it the number of parallel runs. Here I had 5. We'll just reduce that to 3, 4. We're doing 1D. 1D is pretty light on the resources. It can't really even saturate the 2 cores fully. So since we're doing build from DSS, we do have these additional inputs that need to be defined. You have to provide it a template folder, which in this case is our 1D template here. I've been explicit in calling it the template, but this is essentially our submittal as provided, because it only had the 2 plans, 2 geometries, 1 for each event, one for May, 1 for Delta, May 2021 and Delta. So here we've got that defined. We tell it which plan number to use as the template. So whether it's plan 1 or plan 2 or plan 93 that you want to use as your template, you can define that here. And then there's a little bit of logic that's required, since the point of this is keeping everything as DSS files, that we need to be able to provide us input DSS file filtering as well as output, changing the names of those outputs to make it where it doesn't overwrite or try to append that data to the same DSS file, which just is all sorts of hectic. So just to explain real quick, we're going to give it the HMS folder, right? Because in this example, we are linking our HMS to our RAS-1D. So we provided the HMS folder. It's got all of the DSS files. And we provide a DSS search word. Well, in our HEC-Commander script, we make sure that it appends HMS in the HMS DSS file. And that's done for a reason, so that we can use the HMS as the search word. Well, that filters out any other DSS files that might have been used within the HMS folder, right? The HMS will also take DSS inputs. And so if you were to some reason put that in the HMS folder directly, we don't want that to get picked up. So we do want to only pick up things with HMS in the name. We want to replace that HMS with RAS-1D for the outputs, because when we define RAS's outputs, it's not an HMS file anymore, it's RAS-1D. And then there's an additional filter word. And what this allows for is, let's say we ran both of our HEC-Commander events. We had HMS run May 2021 and Delta 2020. Well, then I would have both, and they would both have HMS in the name. They would both get brought into the script. Well, this allows me to just define a single additional word that the script will only copy files that match this word. So for here, I'm using May. That allows me to define an event. Maybe that allows me to define an AEP returnable, or you leave it blank and it returns everything. You just leave it just like this, and it would return everything. But this just allows us to do just enough filtering to get the right HMS inputs for a typical setup, while also ignoring other inputs. If you got good naming conventions, this shouldn't be too big of a problem. And because we're not doing infiltration layer inputs, we've got no infiltration layer inputs down here. So just very quickly, we're going to go through some of these additional settings for Raz Commander. Of course, we need to provide the EXE path for HEC-RAS. Here I'm pointing to HEC-RAS 6.5. I'm not running PSExec in the system account. You need special permissions for that. And so at this point, we're only running the script interactively, which means that to be able to run on remote machines, you need to be logged in as an interactive user, as well as, side by side while running the script. It's a little more difficult, but still well worth it. Eventually, we're going to get those permissions and provide a little more robust operation of the script with system level access that would allow for backgrounding of processes and active thread management. As of right now, if, say, one of the HEC-RAS runs hangs on a remote machine, you may need to reboot that machine or get on and end it. We can't do active thread management because of the limitations of interactive PSExec access. So it sort of is what it is. The PSExec session ID on your remote machine, which I'm actually logged into this machine remote, so I can use this as an example. My user is under session ID 2. That is the default if you're the only user logged into a machine. And so by default, we use PSExec session ID 2, but if for whatever reason yours are different, that needs to be correct. It needs to be correct for all the machines that you're connecting to. It's only going to use one. So if, say, you're connected to 5 different machines and one of them's got somebody else logged on, and your user's actually session ID 3, you may run into issues with the script unless you're running in the system account. So that's all very specific to your setup. If you need more help on that, feel free to reach out. There's also a local target path used in batch file creation. So if you notice, in our inputs, I put my Autoras temp folders on my C drive, just directly on the C drive, and that's the same here on HEC-03. And so if I wanted to get a local path for, if I'm logged into HEC-03, that path actually looks like this. And I have to provide local paths to my batch files when I'm executing things on remote machines. So because that's something I can't detect directly, you do have to provide it. I'd just recommend putting things on the C drive. If you need to bury it in a user-defined folder, that's fine, but you just have to provide the path. If I put this on my desktop, let's say, and I just were to go in here and say create a new folder, I would need to copy that path to that folder. You see what I'm saying? Like I would need to actually put that in here and put an R in front of it. And that would allow it to find the local path. But for the most part, I recommend people just putting that on your C drive unless you really want to make it complicated or your IT wants to make it complicated. You should have admin access to be able to run PSExec on these machines. So anyway, there's a folder safety prefix that is used, say in that temporary folder. If there's a folder that exists that doesn't match the first two letters of the folder that you're working with, it won't touch it, won't delete it. That's just to prevent some accidental file deletions, because it will delete things in the deploy target folders, and sometimes we do get in there and have multiple people using the scripts, and sometimes they can end up in the same folder. That just keeps them from overwriting each other or deleting each other's files. There's a number of file copy threads. You can do some exclusions. If you're doing 1D files, you can add a lot of exclusions here. I've got no exclusions by default because we are doing 2D at one step, but you don't need to copy when you deploy. You don't need to copy PHDF files. You don't need to copy TIFF files for 1D runs, etc. You can define those exclusions here. It'll skip them. It might make things a little faster, but be careful. Sometimes this can make things break because you're potentially, say, if you need the TIFF file for geometry processing and it's a 2D model, then you can break it, and you may not notice that it's buried back here in the additional settings. There's file copy threads. This is the number of threads for the number of file copy threads when it's deploying. This will help speed it up a little bit. Let's see, it's the same as above. I need to figure out which one of these is the correct one. Whenever you're putting in your password, to be able to run things on a remote machine, you have to provide your username and password. So I store the username as a text file. It's in the same folder as your Python notebook. Your remote machine credentials are held in a keyring inside of Python. That way, if for some reason you transfer this script, it's nowhere in your script. The password doesn't go with it. And so this is just a medium security measure to prevent, any weirdness with password handling. But if for some reason you have issues with your password and you perhaps gave it the wrong password, you can always change this service name. It should ask you for your password again and allow you to re-enter it. There's also one other fun little fact. Let's go in here to the Raz-1D template. This part of the DSS path needs to change if it's going from Raz-1D to Raz-2D, but if it's going from HMS, then it doesn't need to override that path. And the reason why is that we never change the run name when we run HMS-Commander, so this run is always the same. But when I run Raz-1D, the DSS path that gets referenced by Raz-2D actually includes the full plan name, so it'll include the run number, DSS suffix, and all that stuff too. So it does have to override it if it's not HMS. So there's a little bit of logic here. I would highly recommend sticking along with that. But this, if you use HMS-Commander, this will happen. So it's all kind of built to be used together. So just understand that if you're not using these file nomenclatures, that you might run into issues. You may have to do a little manual workaround in the script. Okay, so that's it. It's also going to give you a little error if you set the same name as your template file as well as your project file and you're building from DSS, because what that'll do is it'll delete your project folder, which is your template folder, which deletes your template. So it'll raise an exception and it won't do that. That was the last thing in that code cell. So I know that's a lot. That's just the inputs and additional settings. So let's really quickly run through some of the rest of the inputs with the GUI. So we've got our brand new environment. This is just, again, to demonstrate that we auto import and install any necessary tools. It was already done. So, wow, you've got a full GUI. Again, all of the inputs here are pulled from your user input section, so it's highly recommended that you edit things in the user input section. But if for some reason you come back later, you want to run this again, but you don't want to use a remote machine, you just want to use your local machine, well, you can uncheck it, click the green button. This will not persist, but it will work for the one time that you run the model, or one time that you run the script. If I were to change, say, the operation mode there, it would only change for the one time that I hit the green button. And then the next time I open the script, it'll go back to whatever's in the user inputs. But this does allow you to test and quickly iterate through different changes, or if you say, build from DSS, deploy it, and find that 2 of your remote machines are being finicky, and you want to just halt operation, you can hit run all. It'll bring the GUI up. You can quickly go over to run missing, and now you don't have to make the changes in the text. And that would allow you to then fill in the missing runs. So it just allows a little flexibility of inputs, a little flexibility for changes, and allows you to test different inputs without having to deal with that text interface, which can be a little overwhelming. So again, all the same inputs, they're separated. So run missing, this is all that's required for run missing. Build from DSS, this is all that's required. And then if you turn on your infiltration overrides, it gives you those options. So because we're not using those, and we're building from DSS, let's just click out of here. So if anything changed, it gets changed in the variables until you restart the notebook. So as of right now, if I had unchecked them, that will persist. So the next thing that's going to happen is going to check for your PSXEC, which is a tool from Microsoft's Power Toys. So if it doesn't find PSXEC, it will download it from the Microsoft website and unzip it into a folder that you define in the additional settings. But I have it, so here it's going to ask me for my password. Let me put my password in. And it's going to check to make sure that it can successfully connect to those remote machines. So if it does, it's successful, it continues on. If it can't, it's going to keep asking you for that password. And so if you get stuck here, hey, why does it keep asking me for my password? Go try to log into that machine, maybe change your service name to get it to ask for the password again. But I mean, really, it's your username or your password. So try that again and again until you get it right. Or if a specific machine is giving you issues, remove that machine from your list. So start with one machine, add additional machines, do this manually until you figure out what your issue is. Once you get all your machines working and are sort of under your command, then everything should run smooth. Most of the time I don't run into issues on this, but I've noticed new users or infrequent users, people who don't want to open up the remote desktop on all the machines that they are trying to control, they'll run into problems right here. And I actually made it where it will raise the problem here instead of just failing the runs, because that would be the other option, is just to have it fail the runs. And I felt like that was less robust operation. So here it's going to populate all your RAS project name, other paths. And then let's go ahead and go to our folder, because the magic starts happening after this code cell. So because we're in build from DSS, it's going to copy that template folder. It's also going to copy all your DSS files. So let's let it work. It's copying from here to here, and then it's copying all those DSS files from your HMS folder that matched all those criteria you gave it and pulls it in. It also pulls in the existing plans and geometries into a data frame. So if there was 100, it would show 100 here. It's whatever was in your existing project folder, your template folder. So now in the next code cell, it's reading in, again, all those existing plan and unsteady and geometry file associations and making sure to build new plan data for all of those DSS files. So what you'll see here is a very large data frame. I will have to do a little scrolling. I'm set up for a little larger resolution than this. But yeah, all your RAS output DSS file names, unsteady file paths, plan file paths, everything that's needed for all the subsequent steps is built here in this code cell. So that way it can all be checked at once and everything else is just trying to get the data into the right place in the right format. So now that's what happens in the next code cell. If you select build from DSS, it's going to update the plan, unsteady, and project file numbers with short identifiers, plan titles, DSS files, flow files, etc. So let's go to the top of this code cell. So there we go. That's our default plan. That's our template plan. And it's copying all of those plan files and U files and then updating each one of them according to the DSS file name. Again, it's not looking at the CSV file. This is all based on the CSV file name. I'm sorry, the DSS file name. So here we don't have any infiltration overrides, so we run that, but nothing happens. It's going to skip all the logic there. So as of this step, this HEC-RAS project folder is fully built. We've got all of our DSS files. We've got all of our plan files. All the plan files have new short identifiers, new plan titles, new U files defined as the flow file. Here we go. Also, our U files are updated. Got our new DSS file, DSS path is not updated because it came from HMS. And our PRJ file has all of our U files and P files. Now, if we did update our infiltration, we would also have geometry files for each one of those. So, with that, now our project folder is ready for deployment. It's ready to be deployed, copied, and parallel executed. Everything here is just as it was, and so if I wanted to go, or just as it needs to be, so if I wanted to actually go back to the top of the script, clear all outputs, I'm just going to demonstrate the run missing functionality. So we know there's no output DSS files, we just created that folder. And so if you were to run all with the run missing option, it sees all of our plan files, deletes existing directories, and goes. So as of right now, it is, let's pull up HEC-03. I forgot to pull it up. Magic's going to happen before we connect. So you see here on our remote machine, we've got our deploy folder. It's got 3 copies. We're only putting 3 copies on, I think, 4. And so as we watch these complete, first it copies, and then it builds batch files. So it creates absolute path batch files for each plan file in the target directories. So you see here it popped up with these .run files. I'm going to edit this. You can see HEC-RAS is already running. This is the actual batch file that gets executed on these remote machines. If you notice, it uses the local path to the PRJ file, the P file, and then a -C command line flag to run HEC-RAS. So here you go. There's the magic. There's the magic. So we've got a remote machine running for. We've also got our local machine running for as well. So I do believe that we might have the geometry preprocessor on here unnecessarily, but yeah. So this is going to run through, and whenever it's complete, there's an additional step, and I'll just go right through here and show you where it's queuing and executing. Here's where it looks for. It's got the bat file. It's saying, hey, is that DSS file missing? Yes, it's missing. So that's how it comes up with what it's going to run. So it distributes all the batch files that exist among each of the queues, and it starts every few seconds, starts a new run. So here we've got 1, 2, 3, 4 running on HEC-03. 1, 2, 3, 4 locally. So that's our 4 threads, and as each thread finishes, it'll start a new thread in its place. And so we've got 20 runs, 8 slots. It'll do 2 turns, and then the last 4 runs should be split 2 and 2 on those machines. So it handles that pretty robustly, kind of right out of the box. And then results post-processing. So it's not going to post-process the actual results. So once all these threads finish, the results are actually sitting in our remote locations, right? In our actual folders here. And so there's another stage that executes after all the runs are complete. It copies all the matching files, which are your p.hdf, your DSS files, and everything else, replaces them, if newer, into your project directory. So that way, when this completes and the script's done, you should be able to open HEC-RAS, open this project folder, and all of your results are just there. You start with just the project folder, and then you send it out for the runs, and once all those runs are complete, you can close HEC-RAS, let it import all at once, does the results post-processing, which is file copies. And then it deletes those remote locations. It'll ask you to delete those remote locations once it's complete. And that's it. That's Raz Commander. And so you've now seen the run missing mode and the build from DSS mode, and we're going to do one more script after this is done, showing 2D operation with overrides of the 2D infiltration zones, or infiltration parameters, which is something I have not seen anyone else do. So that's going to be a fun one for me. Until then, we'll see y'all later.